Imagine trapping some electric charges inside an imaginary bubble. The total amount of electric field poking out of that bubble's surface is directly tied to how much charge you've trapped inside. That little constant epsilon naught, well, that's just a fundamental number that describes how electric fields travel through empty space. The main idea? What's happening on the surface tells you exactly what's hidden inside.
But there's a catch, and it's a big one. This beautiful equation is only easy to solve when your problem has a ton of symmetry. Symmetry is the magic key. It's what turns this from just a complicated math statement into an incredibly powerful problem-solving tool.
And to use it, we're going to follow the same simple three-step recipe for every single problem. It's easy. Step 1, we look at our charges and figure out their symmetry. Step 2, we pick an imaginary bubble. We call it a Gaussian surface that perfectly matches that symmetry. And step 3, we just apply the law to find the electric field. Let's see how it works.
All right, time to put our method to the test. We're going to start with the simplest source of an electric field you can possibly imagine, a single, lonely point charge. So a single point charge has perfect spherical symmetry. The electric field it creates just radiates straight outwards in every direction, kind of like the light from a tiny star. And, this is crucial, the strength of that field is exactly the same at any point that's the same distance away from the charge.
So, step 2, we choose our tool. And what shape has perfect spherical symmetry? A sphere, of course. So we imagine a spherical bubble, our Gaussian surface, perfectly centered on that charge. Because every single point on this bubble is the same distance away, the electric field has the same strength everywhere on its surface. This makes the math so much easier.
And when you do that easy math, this is what you get. The electric field strength falls off with the square of the distance. Now, if that equation looks familiar to you, it absolutely should. That is Coulomb's law. But we just arrived at using a completely different method and with way less effort. Our shortcut totally works.
Okay, 1 down, 2 to go. Let's level up the complexity just a little bit. What happens if our charge isn't a point anymore, but is smeared out over an infinitely long straight line? An infinite line of charge, which has a certain charge density we call lambda, has cylindrical symmetry. The electric field points straight out from the line, kind of like the bristles on a bottle brush. It doesn't point along the line at all, just straight out.
So what's our tool for cylindrical symmetry? You guessed it, a cylinder. We just imagine a soup can, our Gaussian surface, wrapped perfectly around the line of charge. And because the field only points outwards, it only pokes through the curved wall of the can, not through the flat top or bottom.
So we run the numbers, and here's our result. The field strength depends on lambda, the charge per length. But check this out. The field now weakens as 1 over r, not 1 over r squared like the point charge. Because the charge is spread out in a line, its influence doesn't fade away quite as fast. Interesting, right?
All right, now for our final case, and this one is my favorite because it's so beautifully strange. What if we have an infinite flat sheet of charge? Just a massive, endless charged surface.
With an infinite plane that has a uniform charge density, sigma, the electric field lines have nowhere to spread out to. They have no choice but to point straight away from the plane, perfectly parallel to each other. And this leads to a really wild prediction. The field strength shouldn't change at all, no matter how far away you get.
To prove this, we need the right tool. This time, we use a small cylinder, what physicists often call a pillbox, and we imagine it poking right through the plane. The electric field flows straight out of the flat top and bottom of our pillbox, but it doesn't pass through the curved sides at all.
And here's where it gets mind-bending. The equation for the electric field depends only on the charge density, sigma, and our constant. Now look very, very carefully at that equation. What's missing? The distance. The letter r is completely gone.
Let's just put those side by side. For a point charge, the field gets weaker and weaker the farther you go, falling off as 1 over r squared. But for an infinite plane, the electric field is absolutely constant. It has the same strength 1 millimeter away as it does 1,000,000 miles away. That is a truly bizarre and powerful result, and it's all thanks to symmetry. So, after tackling those 3 big cases, let's put it all together into a simple, practical guide that you can take with you.
And here it is, our complete field guide. For a point charge, the field radiates out and weakens fast, as 1 over r squared. For an infinite line, it radiates from a cylinder and weakens more slowly, as 1 over r. And for an infinite plane, the field is just a constant, uniform force that never weakens with distance at all. three different shapes, three totally different physical behaviors.